The Dawn spacecraft and the Delta II rocket that will launch it depend on each other, but take different paths to the launch pad. Working in separate areas, teams of technicians prepare both the spacecraft and the rocket at the same time. That work started in April, when the Dawn spacecraft arrived in Florida at the Astrotech processing facility near NASA's Kennedy Space Center. Technicians wearing protective coveralls removed the shipping container and covers before inspecting the spacecraft. The Delta II, slated to loft the Dawn spacecraft toward the asteroid belt, started its own preparations at Cape Canaveral Air Force Station. In a hangar a few miles from Launch Pad 17B, workers tested the rocket's instruments and engines. The rocket was taken to the launch pad in stages. There, another team pointed the rocket toward space and began attaching 9 solid-fueled boosters to the first stage. The boosters are crucial to making the rocket fast enough to break Earth's gravitational pull on the Dawn spacecraft. The second stage arrived separately and was lifted to the top of the Delta first stage, where it waited for the spacecraft. While the rocket took its place, technicians at Astrotech ran more tests on the Dawn satellite and bolted on a pair of solar arrays that give the probe a winged appearance. They also readied a suite of sensors and cameras that will let Dawn study the Vesta and Ceres asteroids up close for the first time. The spacecraft was checked out and fueled with the xenon gas before it was attached to the third stage engine, rolled out of the Astrotech hangar, and carried to the launch pad. A crane at the pad hoisted the spacecraft and its protective nose cone beside the rocket before latching it in place.
13, 12, green status board. 10, 9, 8, 7, 6, 5, 4, 3, 2. Main engine start. 1, 0, and liftoff of the Delta II rocket with Dawn, using ion propulsion to reach the catalysts of our solar system.
The kick brake came in on time. Peak chamber pressure this time. Coming up on T plus 25 seconds. This vehicle has worked its way nicely out of the transients of liftoff. Coming up on Mach 1, we've exceeded the speed of sound, and coming up on Max Q. The vehicle is now 3 miles altitude, downrange distance 12 miles, with a velocity of over 1,600 miles per hour.
Listening to telemetry manager Mark Levine.
Both verniers and the main engine chamber pressure still looking good. We're reaching solid motor burnout, the first 6 motors. And burnout confirmed. Jettison, solid motor jettison. And we've ignited the air start motors.
It's so cool going to the asteroid belt, this ring of broken up debris between Mars and Jupiter. These are among the last unexplored worlds in the inner solar system.
It's fragments of explosions of planetary embryos, perhaps, during collisions, or material that's come in from other parts of the solar system and been captured into this orbit of the asteroid belt.
In one sense, it's sort of like our moon, but in another sense, it's sort of like the Earth. It's got an iron core, just like the Earth does, and it may have had many of the processes acting that the Earth has.
Scientists believe Ceres represents a transition from the rocky terrestrial planets of the inner solar system to the gaseous and icy worlds of the outer solar system.
Ceres likely has a rocky core and a very thick ice mantle. There's even the possibility that there's liquid water under the surface of Ceres.
To accomplish Dawn's journey into the heart of the asteroid belt, a spaceship, one whose engine will work without fail for years at a time, is required. Dawn's remarkable ion engines employ electrical currents, magnetic fields, and xenon. The high-tech innards of an ion engine change the xenon into a positively charged plasma and accelerated out the engine at speeds over 78,000 miles per hour.
The ion engine pushes on the spacecraft about as hard as this single piece of paper pushes on my hand. But this very gentle thrust eventually builds up and allows the spacecraft to achieve very, very high speed. With the ion propulsion system, Dawn will be the first spacecraft ever to orbit 2 target bodies after leaving Earth.
We're seeing a shape model of Vesta created by the German Aerospace Center using images from Dawn's framing camera. Vesta is a large object in the main belt with a diameter of 575 kilometers and a shape which bulges at the equator. When we look at the south pole of Vesta, we see a large circular depression, which scientists believe is caused by collision with another object. This depression was also visible in Hubble Space Telescope images, but the features we see now are much more interesting. Flying over this feature, we see large cliffs, deep grooves, and many types of lineaments on the surface. In the northern region of Vesta, there's a large feature we term the snowman, a series of young craters. There are also many variations in brightness on the surface. We see many small craters, grooves and troughs, and bulges as seen in this profile view near the equator of Vesta. There are deep troughs, as well as smaller groove features, and these are telling us something about the history of Vesta, its collisions with other objects, and how the material on its surface has responded. And while these views of this unexplored world are fascinating, scientists are looking forward to the 8 times higher resolution that will be obtained in October from a lower orbit.